This is lecture 2 involving fractional year assumptions, uniform density of deaths, or UDD, and constant force of mortality, or CFM. Both are from chapter 3 of the course Long-Term Actuarial Models. The question I'm going to look at in this lecture has 4 parts, and they all involve finding probability of death or probability of survival using uniform density of deaths or constant force of mortality assumptions. I'm going to do part A on this slide. We're going to use the life table at the right. And first, we're going to find the probability that someone currently age 52.4 dies in the next 0.2 years. And the key for all of these, we'll first put things in terms of survival. So this is 1 minus 0.2 p sub 52.4. And then the key for all of these is to remember that the probability of survival just involves however many are alive at the starting age and however many are alive at the ending age. So this is going to be 1 minus L sub 52.6 divided by L sub 52.4. And then we're going to use each model to find those two. We're going to use UDD first. Under UDD, it's worth remembering that L sub 52.6 is the number of people alive at age 52, L52, minus 0.6 times the number that die between ages 52 and 53. So L52 minus 0.6 D52. And same thing for L sub 52.4. L52.4 is the number of folks alive at age 52, L52 minus 0.4 times the number that die in the interim. Whoops, that should be D52. And D52 is just L52 minus L53. Subtract those two numbers and you'll get that difference is 859. Okay, so the quantity we're looking for is 1 minus L52.6, it's the number we start out with, 89948, minus 0.6 times 859, all divided by 89. So that's roughly the number alive at age 52.6, and we're going to divide that by the approximate number alive at age 52.4. That should be an 859, and that's 89948 minus 0.4 times 859. Okay, and if you crunch those numbers, you should get 0.001917, and it'll be interesting to compare this to the result we get for the exact same quantity under constant force of mortality, which is So the question here is part B. We want to again calculate 0.2, Q52.4. It's going to be exactly the same as before. It's 1 minus the probability of survival, so 1 minus L52.6 divided by L52.4. And all that's going to change is what L52.6 and L52.4 are. And what we need to remember is under fractional year assumption, okay, so for S between 0 and 1, we need to realize the number of folks alive at age X plus X is the probability of survival for the whole year at age X to the power S, and this is in the chapter and in my notes, and it's that times the number alive at the beginning, okay? So that means L under the constant force of mortality assumption, L sub 52, let's do 52.6 first. L sub 52.6 is, well, I guess we need P52 first, the probability of surviving the whole year. P52 is just the number alive at age 53 divided by the number alive at age 52. So that's just 89089 divided by 89948. And if you do that calculation, you'll get that equals 0.99045. There's some more decimal places involved, but we'll leave it at those. Okay, so L52.6 is that number, that probability of survival for the whole year, 0.99405. Raised to the power 0.6 times the number alive at the beginning of the year, 89948. Okay, L52.4, similarly, 405 to the power 0.4 times 89948. Okay. Let's not get our quantities confused here. Okay, so the quantity we're looking for, 0.2 q sub 52.4 is equal to, if we make the ratio of these two in this quantity here, you'll see you'll get 1 minus, and you may 0.99405 to the 0.2, and you may realize things simplified so much here, there are other ways to get to this answer. Some using integration. And for that, I get 0.001917, which is to that many decimal places the same number as what we got with UDD, okay, which may be a bit of a surprise. But just to that many decimal places with these short time spans, they give the same result. All right, on to slightly more complicated questions. So same life table, and this time we're interested in part C, the probability that someone age 52.4 survives 5.7 years. And the key is to realize this just equals the number alive, let's see, 52.4 plus 5.7 is 58.1. So the number alive at age 58.1 divided by the number alive at age 52.4. Okay, so first, under UDD, we have to calculate these two quantities. So first, L58.1 is the number alive at age 58 minus, let's see, 0.1 times D58, the number that died between age 58 and 59. And that equals 83940. Try that again, 83940. Minus 0.1, if you do the subtraction between ages 58 and 59, you get that the number that died between those two ages is 1,221. Okay, and that number is 83,817.9. If you do a similar calculation, you get L sub 52.4 is equal to 89604.4. Okay, so that means that the quantity we're looking for, 5.7 times, 5.77 p 52.4. So the probability a 52.4-year-old will survive the next 5.7 years is equal to the ratio of those two numbers, 83817.9 divided by 89604.4. And when I put those numbers into Excel, I get 0.935422. And hopefully you get the same thing. It'll be interesting to see if this time we get something different using constant force of mortality. So using constant force of mortality, I would like to do the same calculation. So as before, this time under CFM, we're still interested in L sub 58.1. It's kind of nice to see what stays the same and what changes doing these calculations under the two different fractional year mortality assumptions. All that changes is that now L58.1 and L52.4 are calculated differently. Okay, so L58.1 is equal to P58 raised to the power 0.1 times the number alive at age 58. Okay, and if you, so let's make that more complete. So that's L59 over L58 to the power 0.1 times L58. And if you do that calculation, you get 83817.1. Okay, and L52.4 is equal to P52 to the 0.4. That constant force of mortality gets applied for 0.4 years times L52. Okay, and like before, that's L53 over L52. Numbers we can find in the table raised to the power 0.4 times L52. And when I did that calculation, I got 89,603. And undoubtedly, there's a decimal place you want to keep as well, but I don't have that number handy. And when we form that ratio of those two, when we do L58.1 over L52.4, the number we get this time is 0.935423. And it's worth noting that if we go 6 decimal places, there's a difference of 1 in that decimal place from the answer with UDD. So there's not a lot of difference in results for the fractional assumptions, UDD, and constant force of mortality. Part of the reason that's true is because for these years we're looking at, mortality is relatively low. If you had folks in their hundreds, or if you were dealing with a light bulb that's due to burn out in a month, the different effects of UDD and CFM would be more visible. But both are reasonable. This has been Lecture 2, Fractional Year Assumptions under Uniform Density of Deaths, which we're going to call UDD, and Constant Force of Mortality, which we're going to call CFM. And that's from Chapter 3 of the textbook for long-term actuarial models.